Everybody, welcome back to part 2 of advanced counting and the divide and conquer algorithm. So today we're going to be mainly discussing two algorithms. The first one is merge sort and the second one is multiplication of bits. So as you guys might already know, in a merge sort algorithm, the way we sort the list is by first dividing it into two parts. Then we sort each half separately, and then we combine the two halves to form a sorted sequence. So, as we learned in the previous lecture, the form of a divide and conquer algorithm looks something like this, minus the constants. So we're going to try and fill in the constants over here. So we see that we're dividing the list into parts of n over 2. So the size of the divided list is n over 2. And since we're dividing it into two halves, we're going to be considering two separate lists. So we're going to need to multiply this equation by 2. And for the conquer part of the algorithm, we're going to have n here. And this is because in a merge sort algorithm, we take n steps to sort, or rather to combine two sorted lists. This is because one list is sorted and the other is sorted too, but you can't simply combine them because some of the elements in list 2 might be greater than some of the elements in list 1 and some might be lesser. So to combine those, you'll require n steps, and that is the conquer part of the algorithm. So for the next algorithm that we'll be considering is the multiplication of bits. And this is a very interesting algorithm. So let's assume we have a bit, say, something like this. Or maybe it would be better to keep it until elements n. Yes, I think that would be better. So let's assume we have it till n. And same for b. We have it till n. And so to basically multiply these integers, one divide and conquer algorithm that we can use is that we can divide each of these binaries into two halves. So let's say we divide, let's just assume this is a division right here. And so this is going to be n over 2, right? So we're going to have this is going to be the high portion. And this portion is going to be the lower portion. And it's going to be the same way for b as well. So once we have it this way, let's try writing it a little bit more neatly, shall we? Okay. So let's assume we have a, which is equal to 2 to the power n over 2 times a1 plus a0. Now you might ask where this equation comes from. So let's assume that a1 is the higher part of the binary that we considered, and let's say a0 is the lower part of the binary that we considered. And you might be wondering where this 2 to the power n over 2 comes from. But let's assume we have a binary number, say say this is the binary number, and this is where we divide it. And when we've divided it like this is going to be equal to A0, and this is going to be equal to A1. So once we have it this way, we can just add A1 plus A0 because A1 is supposed to be shifted to the left of A0. And since we have n binary digits, we multiply A1 by 2 to the power n over 2, which basically means that we're shifting A1 by n over 2 elements to the left. So ideally, this would look something like, so when we multiply by 2 to the power n over 2, we have 0, 0, 0, 0, and then we have 4 more zeros. And once we're adding it with A1, that changes to 1, 0, 1, 1. So this 2 to the power n over 2 is solely there for the purpose of shifting the elements of A1. And this would be the same for B as well. So now let's multiply A times B, right? Because that's what we're trying to do. So we have A times B. And this would look something like 2 to the power n times A1. Okay, A1 times B1 plus 2 to the power n over 2. Should probably move a little to the right. Yep. 2 to the power n over 2 times A1 times B0 plus 2 to the power n over 2 times B1 and A0. And you can see this equation by simply just multiplying it. You can write B in the same way as we wrote A, so B would be equal to 2 to the power n over 2 times B1 plus B0. And then when you multiply it, you would get this equation. So you can try that out by yourself. And as you can see over here, we're having 3 multiplications, right? We're having to consider 3 multiplications. So immediately you have f of n is equal to, or rather I think this should be f of 2n actually, because we're multiplying, oh no, actually no, you're right, I'm right, f of n, yes, and we're saying 3 times f n over 2 plus c of n, cn. And the reason we have a constant for the Concord algorithm is because this really depends on the size of Cn is really, let me just point this out. Cn is the number of bit operations that we're doing. So this would include addition, multiplication, shifting, and things like that. So based on the size of the binary number, this would really change. So we don't really have a set number of the number of bit operations. So it would really depend on the size of n that we have. And the reason I was considering 2n over here is we could also multiply bit integers of length 2n. The only difference then would be that instead of n over 2, we'd be considering n only, because this would become 2 to the power n because we're multiplying 2n integers. But for this case, since we're only multiplying 2n integers, or no, rather, the way I phrased that out. So we're multiplying n bit integers twice. So a and b. So when we're splitting them, we're going to have 2 to the power n over 2. And since we have 3 multiplications, 1 over here, 1 over here, and 1 over here, we're considering 3, and the size is just n over 2, and Cn is the number of bit operations. In the next video, we're going to be talking about the big O notation and how it applies to the divide and conquer algorithms. See ya.